going to be a slightly different setup today as we talk about improper integrals. Okay, so far we've got integrating these so-called definite integrals over, finite intervals, 0 to 1, 1 to 2, 0 to 2 pi, things like that. But we can now also consider cases where we integrate from, say, 0 to infinity, minus infinity to infinity, or maybe from 0 to 1, but there might be a problem at either 0 or 1, or possibly both. And this is what we mean when we talk about its so-called improper integral. Okay, in this video, we're going to talk about the first type, which are called type 1. Okay, so let's go ahead and mention what we mean when we say type 1 integral. So a type 1 integral is, and these names aren't too standard, but this is, I think, the common convention here. So a type 1 integral is one where we integrate from, say, a to infinity, or perhaps minus infinity to a. Okay, and what's the key here is that we're integrating to either plus infinity or minus infinity, or possibly both. And the idea is that we want to turn this now into a limiting process. Okay, so we have to remember some things about limits, which you should refresh your limits. Watch the limits refresher video series. You'll get a nice basic refresher on some of those limits from Calculus 1 that we may not have seen for a long time. So we have this integral here, 1 to infinity of log x over x dx. We want to evaluate this or show that it diverges. Okay, now here in this context, divergent means the limit does not exist. Okay, so the limit does not exist. Okay, that's what divergent means, okay? Otherwise, we say that the integral is convergent and we assign its value whatever value the limit is. So let's see how to tackle this. Well, we have this integral and we're going out to infinity. So we wanted to go ahead and reduce this to a problem that we already know how to do. Okay, so we're going to go ahead and treat this as a limiting process. So we're going to first treat this as a limit. So the symbol here, the integral from 1 to infinity, okay, log x over x dx. We're going to go ahead and treat this as the limit of some, let's say, finite integral over a finite interval. So we're going to take the limit as t approaches infinity of the integral from 1 to t of log x over x dx. Now, let's go ahead and kind of sketch a picture of what that sort of looks like here. Okay, I'll just draw a rough approximation here. So we have the graph of this function, whatever it looks like. Let's just say maybe it's here. That's 1. Okay. And I think it looks like that. Okay. And the idea is I'm going to chop up this region here, t. Now I want to look at this area here that I'm coloring in. And I want to see what happens as I move that outer boundary out to infinity. Okay. Does this region have some sort of finite area? Does it reach a limit, or does it become unbounded? That's our main question that we want to answer. So we're going to go ahead and treat this problem. Okay, we'll first handle the definite integral from 1 to t, and then we'll go ahead and tackle the limits. Now here, there's a u substitution that we can go ahead and apply here, okay, because we have a function and its derivative. So we're going to go ahead and set u equal to log x, okay, and du is 1 over x dx. And remember, every time that we change variables, we have to change units, we have to change limits. So with that being said, where's my mouse? There it is. Let's give ourselves a bit more room here. Okay, when u is equal to 1, well, then, sorry, when x is equal to 1, then what is u? U is the log of 1, which is 0. And if x is equal to t, that's our upper limit. Well, then u is equal to the log of t. Okay, so now we have our limits here as t goes to infinity of the integral from, now it's from 0 to log t. And what is this reduced to? Well, we have log x is now u, and 1 over x dx, the rest is du. And take a look at that. That's just a power rule, right? That's an integral that we know how to handle. So we still treat this like normal. So this is going to be 1/2 u squared for the antiderivative. Evaluate that between log t and 0. Okay. And now we just do the evaluation step. Okay, we still have this limit here. So we'll have 1/2 of log of t squared, and then minus 1/2 times 0 squared. Well, 0 squared is 0. Okay, so now we just need to contend ourselves with this limit here. Okay, we can go ahead and think about this by looking at a picture, say, using our favorite grapher. Okay, but notice that log t is increasing. The log function is an increasing function. It increases very slowly, but it's increasing nonetheless. So as t gets large, okay, log t gets large, and then I'm squaring that becomes bigger. So this limit is infinity, which means, okay, because the limit is infinity, okay, the integral, okay, that we were looking for, 1 to infinity of log x over x, this integral is divergent. Okay, and that's how we handle improper integrals. Okay, what was the only new thing here? Well, the only new thing here was to handle the limit. That's it. That's the only new thing that we had to do. All right, let's take a look at another one here. Now we have this one here, the integral from minus infinity to 0 of x times e to the x dx. We want to evaluate this or show that it is divergent. Well, now again, okay, we have our lower limit as minus infinity, so we're going to go ahead and treat this as, again, a type 1 limit. Okay, so this symbol here, let's fix that. Okay, where's my eraser? There we go. So this symbol here, okay, the integral from minus infinity to 0 of x e to the x dx. Okay, this will get interpreted as the limit as t approaches minus infinity of the integral from t to 0, okay, of x e to the x dx. Now we look at the integrands. It's x times e to the x, a polynomial against an exponential. Well, the technique to use here is integration by parts. Okay, we're going to use integration by parts here. Okay, and the shorthand, we'll use shorthand here just to save ourselves some time, okay? We can use the DI, or sometimes called the table method, okay, which is a shorthand, not a shortcut, okay? And the idea here is that I'm going to select u to be equal to x and dv to be equal to the rest, e to the x dx, okay? So I'll go ahead and write everything in my table here. So di, okay, let's do this here. Okay, so my u, which is x, goes in a d column. E to the x goes in the other column. Remember, for the table method, we differentiate until it vanishes, then integrate as many times as we did. Now we join these guys here, and then we have tic-tac-toe, right? Plus, minus, plus, okay? And so now we read off our antiderivative very easily. Okay, we still have this limit here. Remember, anytime you do a limit process, and that should be minus infinity, anytime you're doing any kind of limit process, you have to carry the limit operation through until you're done, okay? So we have this limit as t goes to minus infinity of, well, let's read it off here, x e to the x minus e to the x. This is going to be evaluated between 0 and t. Let's go ahead and write everything down for the evaluation step. We have the limit step, okay? And now we have 0 times e to the 0 minus e to the 0. Well, that's going to be nice. And then minus, well, we'll just replace everything here with a t. So t e to the t minus e to the t. Okay. And now let's just go ahead and clean up here. Again, that should be minus infinity. Okay. So the first part, we have 0 times e to the 0, that's 0. Minus e to the 0, that's a negative 1 there. And then minus t e to the t minus e to the t. Okay, we're going to have to remember some properties about our infinite limits here. Okay, and we want this as t approaches negative infinity. Okay, so once again, watch the limit refresher series. Okay, So what we'll notice here, okay, let's make a note here. Notice that e to the t goes to 0 as t approaches negative infinity. Okay, so what does that mean? So this last term here goes to 0. This middle one also goes to 0. Okay, because we'll have a polynomial against an exponential, and the exponential gets small enough faster than the polynomial. Okay, so all of this goes to 0. And what are we left with here? We are just left with a -1 there. So the limit is -1. And so in this case, we say the integral is convergent. So the integral is convergent, and we assign it the value of -1. Okay, so that wasn't the case where the integral actually converged. Okay, and notice that we had to use a familiar integration technique here, integration by parts. Okay, we did it with the table method. You can go ahead and fill in the classical variation here with the UdV formula. Okay, that's the formula that we still need to remember. All right, let's look at our last type 1 integral here. This one's a fun one. Okay, the integral from -infinity to infinity of 1 over x squared plus 9 dx. Okay, now this is actually one of my favorite kind of integrals. Now notice here that both the upper and lower limits here, okay, go out to both infinity and -infinity. So we can actually go ahead and assign this, okay, a sort of one way, one variable limit here. Let's draw a picture to show what I mean here. This function kind of looks like this. It's not quite a bell curve, but sort of a bell curve. And we're going to go ahead and say, chop this up from -t to +t. So we have this area here. And I want to go ahead and stretch this out all the way to infinity. Okay, so this integral, we're going to interpret this symbol. Okay, going to interpret this as the limits as t approaches infinity of the integral from -t to t of 1 over x squared plus 9 dx. Okay, so this is one where we have to remember one of two things. We can recognize immediately that this is an arctan integral. It is an arctan integral, okay? Or we can just go ahead and use the trig substitution. I'm going to go ahead and make this practice, that trig substitution, just so we see it again. Okay, notice that we have a sum of squares, x squared plus 9. So we're going to go ahead and let x equal, say, 3 tangent of theta, but I'm just going to call it tangent of y. It doesn't really matter. So dx is equal to, well, derivative of tangent of secant squared. All right, now take a look at what happens here, okay? Remember, we change variables, so we change limits. So when x is equal to t, okay, so we need to find the y for which t is equal to 3 tangent y. Okay, but now if I shuffle and do some stuff with the inverse operations, okay, divide by 3, take the arctan, so I get y is equal to arctan of t over 3. Okay, and we'll also get a similar one for -t, okay? So if x is equal to -t, okay, then we need -t to be equal to 3 tangent of y. And in a similar fashion, we get that y is equal to arctan of -t over 3. Okay, so let's go ahead and plug everything in here. So we still have the limit as t approaches infinity, okay, of this integral from arctan of -t over 3. Let's fix that there. To arctan of positive t over 3. It's getting a little cramped, okay. Dx here is just 3 secant square y dy. On the bottom, okay, we have 3 tangent y squared plus 9. Okay, I'll spare you the details here. Okay, but when we go ahead and clean everything up here, we'll have arctan of -t over 3 to tangent inverse of t over 3. Okay, when we clean up everything here, look at the bottom of that fraction, right? 3 tangent y squared is 9 tangent squared y. I can pull out the 9. Okay, well, you know what? Let's go ahead and write it down. 3 secant square y dy. Okay, 9 times tangent square y plus 1. Okay, after I factor everything out, and now take a look here. Okay, secant squared is 1 plus tangent squared. All right, so we're in business. Okay, I'll have a 1/3 that comes out of here. So we'll have this limit. Okay, this integral, arctan of minus t over 3 to tangent inverse of t over 3. All right, we have 1/3 dy. Huh, okay, well, that's nice. Okay, well, that 1/3 is like a 1. Okay, I can shove it out. And if I'm just integrating dy or dx or whatever, okay, where it's just a constant inside, it's just the length of the interval. Okay, when we do top minus bottom here, okay, when we use the fundamental theorem of calculus, okay, let's write out what we have. So we have 1/3 of y. Okay, let's just go ahead and write it out for completeness sake. Okay, evaluated on the boundary. Okay. And now we have this, okay? So we got to think about the limit for the arctan function here, okay? 1/3 arctan t over 3 minus 1/3 arctan minus t over 3, okay? Now, we're going to have to remember something about arctan here, okay? Arctan t, okay, or rather, let's write arctan u, goes to what as u approaches infinity, okay? So as u approaches infinity, arctan approaches pi over 2. And as it approaches minus infinity, it approaches minus pi over 2. So that's helpful, right? Okay. So now when I apply that here, okay, let's go ahead and just make a note of that here. This will go to pi over 2. This will go to minus pi over 2. And so plugging everything in here, and I can factor a 1/3 out, okay? We have a 1/3 times pi over 2 minus a minus pi over 2. Well, minus times minus is plus, okay? So I get a pi on the inside there, pi over 2 plus pi over 2. And what do I get here? Just a nice pi over 3, right? Okay, the integral converges. That's all there is, okay? So the thing to remember with these improper integrals, okay, is to remember that you're just doing a limit process, okay? In this case, for a type 1 integral, we're trying to reduce it to a finite interval and then stretch out that interval to infinity, okay? We have to remember some of those basic limits, okay? How arctan, e to the x, and log behave, okay? Thankfully, we haven't had anything too crazy here, all right? But in the next video, in the next part 2, we're going to talk about now a special type of integral, the type 2 integral, where now we're integrating either to or through a discontinuity. So some of that Calc 1 stuff's going to have to come back, right? I'll see you in the next one.